High five, guys. High five. Can't find you? Yeah, no, that's fair one. I see your phone, it's not on the desk because it's 24 hours. Right, you can. But then we work properly. So if you misbehave, not a minute. Right. Okay. So a reminder, how does deduction work? Okay, what's the logic? First of all, okay, don't write this down, you know. First of all, induction is really only working with natural numbers, proofs for natural numbers. Okay. And first thing you have to do, okay, or it can be integers as well. Okay, so it's using natural numbers. First thing is we have to show that the first domino falls over. In other words, you have to prove your first step is going to be prove true for usually for n is equal to 1. Sometimes it's like n is 2 or something. And then on separately, okay, you do something else. What do? We assume that if a domino falls, the next domino will fall. Okay, so assume that if some random domino falls, the next one will always fall. So we assume, okay, if true for some random natural number, we make an assumption, true for n is equal to 1. Okay, we assume that if true for n is equal to k, where k is some natural number, and then the actual proof part of the sum is we then prove true for the next natural number, which will be what? Someone time half an hour for me. Make it, yes. No, because you give me the last 10 minutes off. Prove true for n is equal to k plus 1. No, we'll stop at 11:50, 40 minutes. Okay, make it 40 minutes. Okay. So we assume that if a domino falls, the next one will always fall, right? Yeah. Okay. So now we combine those two bits. Okay. And what's the result of combining those two bits? Well, we proved that if one falls, the next always falls, and we proved that the first one falls, right? In other words, if the first one falls, what will happen? The second one will fall, the third one will fall, the fourth one will fall. In other words, they'll fall ever for all natural numbers, right? Okay. So your final step then is this concluding sentence where you say, therefore, okay, blah, blah, blah. You're going to always write this final sentence. You're going to say, therefore, true for n is equal to k plus 1, given true. Are you also quiet? Because you've got a test. Given true for n is equal to k, and true for n is equal to 1. Don't write this down in your notes. Okay. Therefore, true for all n is an element of natural number. That symbol, upside down A. Oh. Okay. Is that not right? Thank you. Okay. All right, no, not matches, generally chaotic. These are sort of on. And they were off, and then I don't know, they're taking, and most are going to take like a good snap of Coke at lunch. They were off, they were off their heads. Yeah. That is. Don't worry about that. Okay, right. Let's go to this one. I'm going to write it down 1,000,000 times. Okay, right. So there's a video you can watch, man, and you can read through those notes up to page 4. Okay, but if you can do what we're doing today, you'll be fine. Okay. Okay, right. Then your arms against the chair. Understand that? Your back against the chair. Okay. Breathe. Okay, right. Okay. All right. So, right now I need attention. Okay. Even if you're eating popcorn. Right. Okay. So it says, prove that 2 plus 4 plus 6 plus 2n. In other words, that it's saying prove that the sum of the even numbers of the first of n even numbers, that's what that's saying. Prove that the sum of, you don't have to write this down if you don't want to, but this is what the question's asking. Prove that the sum of the first, that says first, n even numbers is equal to n times n plus 1. Okay. Why is that helpful? Because if I said to you, in other words, so if we can prove this, we could say something like this. If I said to you, what is the sum of the first 100 even numbers? Okay. So if this was true, if this proof over here was true, so tell me what that would be. Come on. That statement was true, what does that be equal to? I'm not expecting you to go 2 plus 4 plus 6 plus 8 plus 10 plus 12. How are you going to work it out? If this is true, the sum of the first n even numbers, that's what this is saying. Sum of the first n even numbers, up to position n, right? So the sum of the first 100 even numbers, so n would be equal to 100, would be equal to what? Come on. This is saying the sum of the first n even numbers is equal to whatever n is. In this case, n is what? 100 times 101, which is whatever that is. Okay, which is a lot quicker than going 2 plus 4 plus 6 plus 8 plus 10 plus 12. You with? Yes, that's what that question is asking. Yeah, but we can't ever assume something in math that statement is true. So how do you prove something like that? Well, if you're working, so first of all, induction only works for natural numbers and integers. Okay. So the first thing is we have to prove, what about dominoes? That somehow we can push the first one over, right? In other words, we're going to prove the statement is true for n is equal to what? Okay, so it's a very structured kind of proof. Okay, so you're going to say, which is good in some ways, because normally questions are like out of 12 marks. And 6 marks, blah, 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 blah. 6 marks, basically the regurgitation. Okay, and 5 marks is a bit of thought. Okay, so you're going to start this always by writing for n is equal to what? Well, the left-hand side of the equal sign, what does that mean on the left-hand side? It means what is the sum of the first 1 even numbers? What's the sum of the first 1 even numbers? 2. Okay. So it's just 2 plus nothing, right? And if you want, you could say 2 times 1 is 2. But the question is saying, what is the sum of the first even number? First even number is just what?
2.
2. Because it's a sum, you're adding 1 even number. If I add 1 even number, just 2. What will be the sum of the first 2 even numbers?
2 or 3.
First 2. Okay, let me just show you what we're talking about here. Okay, so the left-hand side, let's just get this notation one. If n was equal to 1, what would the left-hand side be? If n is the left hand of the equal sign. In math, left-hand side means left hand of the equals. Okay, so when n is equal to 1, what's the left? You're going to add the first even number, which is just 2. What would be the right-hand side? So this is part of the proof. We're going to do that here. Right-hand side would be what? Well, you're going to sub in n is equal to 1, right? So it'll be 1 times 1 plus 1, which is equal to 2. Okay, yeah. This bit on the right, you don't have to write. This is what you write. Anything to the left of this line, you write. I would for the right-hand side. Okay. Just to show you that this is working. Yeah. Okay. If n, let's just see if this, if you understand this. If n is equal to 2, what would the left-hand side be? 6. Why? Because you're adding the first 2, right? It would be 2 plus 4, which is equal to 6, right?
Which you have to say equal to.
But no, you're not writing this down. I'm just showing you that this is working. Okay. Because if we could show that it didn't work for 2, well, then we're wasting our time. Do you agree? Okay, what did the right-hand side be? I replace n with 2, right? And I get 2 times 2 plus 1, which is 2 times 3, which is? Okay. So is it working for 2? Okay. What about 3? No. Okay. If n is equal to 3, what does the left-hand side be? The sum of the first 3 terms, right? Which would be 2 plus 4 plus 6, which would be 12, right? The right-hand side either would be what? See, if it's going into a coma. Okay, it would be 3 times 3 plus 1, which is 12. So it appears this is a possibility that this thing will work. Proof, I could show this a million times, it proves absolutely nothing. Because maybe the million and first time doesn't work. Mathematical proofs where you show things over and over and over again mean nothing. You can make an hypothesis based on that repetition, but proofs have to be done algebraically. Okay, so it looks like this could work. Okay, so for n is equal to 1, we've done that first part. What have we shown in terms of dominoes, Rosie? We've shown the good that the first one can be knocked over. Right.
Is that all?
That's all we've done so far. Okay. But now we're going to show what? That if one, no, that if anyone falls over, that's good guess. If one, we assume that if one random one falls over, the next one will fall over. Right. So we start with an assumption. Okay. So this is the first part of the proof. And you've got to write this down. Detailed matters here. That's 12 marks of this question. 1 mark. Okay.
Yeah.
Right. So the next thing we do is the next part of the proof is we make an assumption. In other words, we assume that we just knock over some domino. Assume true, if I cannot speak English today, for n is equal to k. Where k is has to be what type of number? A natural number. If you do not write that, I take off a mark. Yes, what I write, you write. Okay. None of this is optional. Okay, to the right of this line is notes. Assume true for n is equal to k, where k belongs to the set of natural numbers. Now we write the assumption mathematically. Okay, so we say i.e. we assume what? That the sum of the first k terms, k even numbers, is equal to k times k plus 1. Okay, in other words, we assume 2 plus 4 plus 6. Come on, Roger, be better. 2 plus 4, maybe I need to speak in Russian, plus 6 plus 2k. That's not Russian, I don't know what that is. Okay, is equal to, think a bit of Russian so I can get into it. It's equal to what? Okay, so what was that? That wasn't Russian. K times k plus 1. So we're going to, what are we assuming? We're assuming you knock out the sum domino. Okay, right?
Wait, what is this? That's the second domino.
No, we're assuming now. We stop part 1. Almost like a full stop here. Okay? That's the assumption that the first domino falls. Now, what's this saying mathematically? We assume some domino falls over, right? Okay, some domino, we don't know where it is, but it falls over. Stay with it. Now what we're going to try to prove, I want you to always put a star here, and I want you to highlight it, this assumption. This is, because we have to use this when we do that actual proof. Text box is not opening. So we're going to, okay, so I'm still struggling to open this up on the page again. Yeah. Right, would you like to highlight it? Yeah, you can have a first spread. All right. Okay, so now, okay, so we assume that. Okay, right, okay, right. Now, what I have to prove? What I have to prove? What are we trying to prove? That if one drop domino falls over, keep on your way. That's one drop for today. Okay, right. After that, stand up and go. After that, stand, go wash your face. Go, go. You're not going to make it. There's not a chance in hell. Okay, right. Okay. So then it's required to prove. And again, are you going to write this? Yes. Okay. We're trying to prove, we're going to try set out and prove that it's true for A. Yes, you have to write that N is equal to K plus 1. Yes, and when I write, you write. I don't know what it is. Yes, step 3. Okay. In other words, mathematically, what do we have to prove? That the sum of the first K plus 1 terms is, so basically now I replace N with K plus 1. I'm trying to prove, I assumed a domino falls over. So I assume the start of the proof is saying, I assume some random domino falls over. What do I then have to go do after that? I have to prove that the next domino, based on that assumption, will always fall over. Don't have to write on the right here. You do not have to write. Will always fall over, right? Okay. So what's required to prove, i.e., mathematically required to prove, is going to be what? 2 plus 4 plus 6 plus. You must write down the k bit over there. So plus 2k. What will be the term of that's up to k, right? So the next one will be plus 2k plus 1. This is what I'm going to try to prove. Is going to be equal to what? Is equal to, I'm replacing n with k plus 1. I'm going to try to prove that this, so I'll replace k with k plus 1. So that becomes k plus 1. Okay, that's that one over there. You with me? Because I'm looking at the sum of the first k plus 1 terms. Okay. So that's the sum of the first k plus 1 terms will be equal to k plus 1 times what?
K plus 2.
Good. Times k plus 2. So this is what I'm going to try to prove. Where did
you get the second 2?
This one.
K plus 1.
This one. Because this is the sum of the first k even numbers up to position k. Now we're going to prove it up to position k plus 1. So that's the sum of the first k plus 1. You with? Okay? And here that becomes k plus 1. That becomes k plus 2. Because that's the term before. This is when k is equal to 1. 2 times 1. This is when k is 2. 2 times 2. This is when k is 3. 2 times 3, right? This is when n is equal to k. So that's 2 times k. This is the next term, which is 2 times k plus 1. It is. It's 2 times k plus 1. What is 2, Emma? 2 times 1. What is 4? 2 times 2. 6. 2 times 3. The term in position k will be 2 times its position. The term in position k plus 1 will be 2 times position k plus 1. Kavish? Okay. Right. Now, okay, so that's the sum of the first k plus 1 even numbers. And we're trying to prove it's equal to k plus 1, k plus 2. What am I doing again? A reminder. Okay, we assumed if a domino falls over. What we're going to try to prove now? That the next domino will always then fall over. To do that, I've got to prove this thing over here. RTP means what? Okay, so I'm going to try to set out and do that. Now, okay, so you have picked up marks just for being able to regurgitate, okay, a pattern, a step. You've got like 4 marks up to this point, right? Now, you have to do a bit of actual mathematical thinking, and again, it's not that difficult. Okay, so your proof, I write down proof, but this is now we're starting to do some math. Okay, what are we trying to prove? The left-hand side is equal to the right-hand side. Like all proofs, like you did identities and tricks, sometimes we just work with the left-hand side. Sometimes we work with the right-hand side. Sometimes we work with both. But we have to get that equal to the same thing, right? But you definitely, in this proof, you're going to have to force this star, into that proof. Okay? Because this proof is based on this assumption. Okay, assuming some random domino fell, right? We've made that assumption. We've got to use that assumption in the proof. Make a note. Must use star in the actual proof part of the sum. Okay, star was this bit over here. There. Fish. Right. Okay. So my proof. I start with the left-hand side. Stay with me, Eva. Okay. The left-hand side, okay. Right. It's this whole thing over here, right? So I just rewrite the left-hand side. So the left-hand side is 2 plus 4 plus 6 plus ... plus 2k plus 2 times k plus 1. But now, guys, immediately I'm going to use my assumption. Here is my assumption, right? What's that equal to? K times k plus 1, right? From the assumption. Okay. Because remember, we're assuming a domino falls over. So I'm now going to use the fact that a random domino falls over. Stay with me, Boris. Right. Okay. So I'm going to sub in star here. Okay. So I'm trying to prove this. What I've circled here in yellow is what I'm trying to prove, right? Okay. So I've taken the left-hand side. What I have to prove is equal to the right-hand side, right? So the left-hand side, I just rewrote it. But here, you've got to keep looking at, this is why I said highlight this bit over here. You've got to keep looking for your assumption, right? You've got to use the fact that a domino has fallen over. So 2 plus 4 plus 6 plus 2k, there it is over here, voila, okay? We know that that's equal to what? K times k plus 1, right? So I replace this with k times k plus 1. So now the left-hand side is equal to what? Tell me. That's 2 times. You still got that bit over there, right? That was over here my assumption, right? No, I'm thinking, no, not k times k plus 1. Yes, k times k plus 1, sorry. Okay. Are we happy with that? Keep an eye on the right-hand side. What are we trying to prove that's equal to? K plus 1, k plus 2. So there are 2 ways you could do this. If you wanted to, you could take the right-hand side and you could times it out. And you could, and then times out and show that the same. Or you can say, how many terms are there? How many terms? There's a common factor of what?
K plus 1.
So go take it out.
Oh, yeah. Take it out of what?
I was going to say. Okay. So, we're going to factorize, right? So what's the common factor here? K plus 1, right? What I've times k plus 1 by to get back to that? Okay, to get back to that term? Which is equal to the right-hand side. It would have been perfectly fine, as I said, AA, if you had times this out and got some trinomial, 3k squared, whatever it is, and times that out and got another trinomial, okay, we'll be fine. Okay, but that's pretty. Okay. So now, all right, so this is what the proof part of the question. Okay, probably got 4 marks for that. So you've got 6 for all that crap in the beginning, 4 for that. You stop there, you get 10 out of 12. Okay, right. But why not get 12 out of 12? Okay. So this is going to be your final sentence is every single time you're going to squeal and moan, unlucky. So you're then going to say, therefore, true for n is equal to k plus 1 given true for n is equal to k. Okay. Isn't there any comment? And true for the first domino, basically saying the next domino will fall over if one falls over, and it's also true for the first domino. What does that mean? All the dominoes fall over, right?
Yeah.
Therefore, true, what's upside down A, what does that mean? For all, n is an element of, and now we can do one little summary by PMI. Principle of mathematical induction. What is that 9? N is an element of natural numbers. How's your comfort pig treating you? Is it helping? Okay, fantastic. Comfort pig. Prove that this statement is true. That no, they didn't. It said prove that. It said prove that. They didn't tell you that. Well, we proved that it always will be true. That's what matters.
So is it ever not to do that?
No, they say prove that. Okay, then it is true. If the question says prove that, then you got to prove it's true, right? If it says to you, hey, is this true? Then you got to try and show that it's true or not true, which we would not do in this
It's
section.
just a trick question, but they said.
No,
And they're not Roedean.
no.
We give it to that.
It's like a geometry proof, guys.
So if we give it some formula, can I just say it's not true, then she'll.
Okay, all right. Are we good? Okay. Everyone stand for 30 seconds. Stand. Stand. Right. Stand. Put your right ear, sorry, put your right hand on your left ear. People struggle with this. Right hand, yep, here we go. Right hand on left ear. Okay, left hand on right ear. Okay, right, jump up and down. Okay, right. Okay, put your right hand on the person next to you's left ear. Right. Okay, now walk like an Egyptian. That's how Egyptians walk. Okay, right, sit down. All right, okay.
No, not good enough.
Yes. Hello, let's see if anyone listens to what I say. Principle. Yes. No, of course it makes sense. Okay, because why? We say, assuming one falls over, okay, will the next one fall over? That's what we prove. So based on the assumption, we say, okay, I don't know, but let's assume one does fall over. Maybe it doesn't, but assume one does fall over. It doesn't. Assume one does fall over. Okay, we're not sure if it does, but we assume it does. Some random one falls over. We then prove the next one will always fall over. That does not prove this proof. Without first showing what? That it's true for n is equal to 1. Because you have two separate parts of the proof. One says assume something falls over. Okay? Make an assumption that somewhere in that whole set of dominoes, one falls over. Say make an assumption. Okay? Then go through the next one will fall over, right? Based on that assumption. That would not prove anything by induction. You have to then show, or first show, that the first one can fall over. Okay? But then you prove that if one falls over, the next falls over. So if the first one falls over, and we prove that if some random one falls over, the next falls over, then the second one will fall over. You're combining those two parts of the proof. Okay, not I suppose. Okay, right. Okay, it's true. It's pretty simple, the logic in some ways. Okay, but the one doesn't exist without the other. Okay, you have to have that first domino falls over. So the first domino falls over, and you separately you prove Assume a random one falls over, the next one will always have to fall over. Combine those two bits, then the first falls over, the second will fall over, the third will fall over, the fourth will fall over. And you proved it's true for all natural. Give pure math advice. Pure math is proof. It's a lot of this kind of thing. Okay. It's detailed because that's how we build up knowledge, right? Also not to do pure math in uni. Okay, right. But I do think they do this even in some commerce courses. Because it's logic. Philosophy, if you do philosophy, you're going to do this stuff. What's going on here now? Yeah, thinking. Okay. So we had an example. What does that example? What? Where's example 2 gone? Oh, there it is. Okay. Right. So now, Emma, you're going to stress? Okay.
What's the beginning of that example? For any one,
Okay.
what is equal to?
No, left-hand side means if n is equal to 1, it means what is the sum of the first 1 terms?
What do you mean by the n is equal to 2?
So,
It would be 2 plus 4 equals 6, and the right hand side is equal. If n is equal to 2, it would be 2 plus 4 plus 6. The right hand side is equal.
Right.
So you're saying 2 because that's the first term. Yeah.
Okay. Right. Now, we had a little thing on sigma notation. Read for us, Boris. What does it say here?
Endlessly. Always rewrite the question by getting rid of sigma notation by explaining.
Okay, so if you get a question, Eva, with sigma notation, you want to get rid, Ria, of that sigma notation, right? Okay, before we even start the proof. Okay, so this is your sigma notation. Okay, so we're going to expand that sigma notation. Somebody explain to Emma how we do this. Okay, what's the bottom number, Rosie? The first number you sub in, right? What do you sub into? You sub into this. I'm going to give you a head slap for it. Okay. Right. What is this over here? The last number you sub in. Boy Jamal, tell me please. Hey, what's this? It's you. Yes, capital sigma. What does it mean in math? What's the sum of? Okay. So the bottom number is your first number you sub in. Okay. What type of numbers are we working with? Integers, right? Not fractions, right? First number you sub in, okay, into that formula. Last number you sub in, right? Sigma means go and add them up. Okay. So, what's the first term going to be? Okay, you don't have to write that. Step 4 times 1 minus 1. That's the first term. The first number I sub in is 1. Okay, I've got to add them up. So it's going to be what sign in between? Plus. What's the next term going to be? Yes. So this is an expanded version of that sigma notation. So what's it going to be? 4 times. What's the next term going to be? 4 times 3 minus 1. Okay, that's more than enough. Plus dot, dot, dot. And Rosie, what is the last term going to be? I thank you, Rose. Okay, right. Plus 4n minus 1. Boris, you with me? Right. That's right. Where's your mouth? Because look at it. Always heading off to the airport with a little cake. Okay, right. What's another Russian name?
No, this is yours. I'm Gulash.
You can be both.
I think it's
Okay, you're Milos.
I'm Gulash.
Gulash. Gulash and who are you? Milos. Gulash and Milos. Milos and Gulash.
Yes.
You feel a little more Czech than Russian.
Yes.
I'd like to be Vladimir. Vladimir. Or just Relado. No, that's too water polo. Okay, right, okay. All right, so this becomes what? So this series is in fact what? 4 minus 1 is 3. You can go straight to the step. So it's 3 plus what? 7 plus, we're going up in 4s. Remember what that number is you're going up in. Plus, dot, 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 plus 4n minus 1. Okay. So if you get a question on segmentation, you get rid of the segmentation and then start the question again. Kabish? You can skip the middle step. Okay. So what is the question that we're trying to prove? We're trying to prove now that required to prove 7 minutes, we have to finish the sum overall for the whole. I know we haven't started induction yet. We're just rewriting the question still at this stage. So the question is saying, go prove that what? Okay. So I'm going to say prove that. I'm going to rewrite it, but otherwise you'll think which RTP are we working for? Prove. So the question is saying, so the question in non-sigma notation is saying this. Prove that 3 plus 7 plus 11 plus dot, 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 plus 4n minus 1 is equal to 2n squared plus n. So this is what we're trying to prove. Yeah. Okay. Now we forget about the segmentation. So now we're starting the induction proof. So what's the first thing we have to prove? That it's true for n is equal to 1. Okay. So for n is equal to 1, what does that mean? Okay. Add up the left-hand side, right? What is the sum of the first 1 terms? Okay. If n is equal to 2, what does the left-hand side be, by the way? Don't write this down. If n is equal to 2, the left-hand side would be 3 plus 7, which is 10, right? Okay. For n is equal to 1, though, the right-hand side is what? You sub into this formula, right? So it's 2 times 1 squared plus 1, which is 3, right?
Yeah.
Okay. What does the right-hand side be for 2? 2 times 2 squared plus 2, which is also 10. Okay, so it's working. Right. So n is equal to 1. Okay, so what I say now? Therefore, true for n is equal to what? First of all, I finished that.
We didn't do that way.
No, we did finish it off with therefore true for n is equal to 1. No, we should have. Sure we did. Should have said therefore true for n is equal to 1. Okay. Right. The next step is now we assume what? So we've shown that the first domino falls over. What do we make an assumption now? We assume what? We assume that some domino falls over. Assume true for n is equal to k. What kind of number is k? Natural number. We have to then say our assumption mathematically, i.e., we assume what? What do we assume? We'll just replace n with what? Okay. So we assume what, Rosie? What do we do now with this? Put a little star and you highlight it. We have to use this when we do our proof. No. Okay. Kabish. Right. Now what? We've got to prove it's true for the next one, right? So required to prove what? True for n is equal to k plus 1. So in other words, mathematically, what we're going to try to prove? 3 plus 7 plus 11 plus the kth term will be 4k minus 1 plus, what's the next term going to be? 4 times k plus 1, I replace k with k plus 1, right? Minus 1, right? That's the k plus 1 term. You agree? And I'm going to show it's equal to what? 2k plus 1 squared plus what? Plus k plus 1. With me? Come with me up to this. What I have to use when I do my proof now? I have to use my assumption, right? That I'll solve it. Right. So my proof. Yeah. Because I'm replacing k with k plus 1. Yes, I'm replacing k with, I'm showing it's true for the k plus 1 term. So the original statement was k, 2k squared plus k, right? That's what we're assuming it's true for, right? Now that's for the sum of the first k terms. Now we're doing the sum of the first k plus 1 terms. Okay, so you've got to replace k with every k with k plus 1. Then this is a different notation here. Okay, because this is saying that this is term 1, term 2, term 3. This is term k, right? This is term k plus 1 over here. We're saying the sum of the terms, okay, that's term 1, term 2, term 3, okay, is always equal to what? 2 times the number of terms squared plus n. Okay, 2 times the number of terms now is k plus 1. Okay, all right, you with? Okay, now what? Now I do the proof. Okay, and what I have to use in the proof, I have to look for this thing over here, right? Is it there in the sum? It's that bit over here. It's over here, right? So proof, you're going to say the left-hand side is equal to 3 plus 7 plus 11 plus 4k minus 1 plus 4 times k plus 1 minus 1, right? Finish? That's the left-hand side. What am I trying to show it's equal to? 2 times k plus 1 squared plus k plus 1, right? Is the assumption in this left-hand side? There it is over here, right? There's your assumption. There's that bit over there, right? So from star, what does the left-hand side become? So from star, this left-hand side becomes equal to 2k squared plus k. That was this yellow bit over here. But I've still got this bit over here, right? Okay. So plus 4 times k plus 1 plus minus 1. I think the quickest thing here is going to be to times that out and then to work with the right-hand side and times that out and show that they're the same, right? This is the left-hand side. Our right-hand side is equal to 2k plus 1 squared plus k plus 1. So if I simplify the right-hand side, I get 2k squared plus 2k plus 1 plus k plus 1, which is 2k squared plus 4k plus 2 plus k plus 1, which is 2k squared. The other way you could have done this plus 5k plus 3, right? Okay? That's the right-hand side of what I was trying to prove. K squared plus 4k plus k. And the left-hand side becomes 2k squared plus k plus 4k. Yes, I know. Here's the plus k plus 1. With me. Which is 2k squared plus 5k plus 3. So what have I shown? Therefore, left-hand side is equal to right-hand side. And then you're going to write that whole last sentence down again. Therefore, true for n is equal to k plus 1, given true for n is equal to k. And true for n is equal to 1. Therefore, true for all n is an element of natural numbers by PM. Right, sorry, for 7 minutes. So I worked with a reminder. Okay, so I had to prove, okay, for the left-hand side, I took the left-hand side, I did the substitution from my assumption, okay, and I got left-hand side of 2k squared plus 5k plus. Okay, the right-hand side was over there, right? That's what I'm trying to prove. So I just simplified the right-hand side, and I showed that the left-hand side and the right-hand side simplified the same thing, so they must be equal to each other. So this over here was what I set out to prove in the beginning. Okay, well, in the next part of the step, yeah. This is what I was trying to prove. So I worked with the left-hand side of that and the right-hand, that is the right-hand side of that. Okay. All right, Thomas, Fabian, good luck for your final test.
Why? Whatsoever. You may begin. You have 60 minutes. Good luck.